much, Tim. Yes, so I'm going to talk about what we're doing in Edinburgh. This is part of the core funding and consequent and related funding. So it's not just my work, it's other people's work as well. So the first thing, Matt was saying that we've done time domain array modelling. So I'm just going to update you on the work that we've been doing within that. So we just had this published this year on the wave-to-wire model. So we've been updating that. My colleague Anuk Nambiar has been doing this. So we've now included within the wave-to-wire model, we've included a better generator. So we now have a vector-controlled generator, and that's good. We no longer have a fixed speed generator. It allows us with greater flexibility of control. We can do speed and torque control, so it's independent of the hydraulic power takeoff unit, so it improves their performance. So here's some results of doing that. So on the left here, we can choose to have our generator running at whatever speed we want. Here we've chosen to have it running at 0.5 per unit, which is 0.5 of its nominal speed. You see the torque curve up there. On the right-hand side, your right-hand side, yeah. You'll see we ran the code for a number of C states, and we found that depending on the C state, we could pick the optimal generator speed. Okay, and then at the bottom graph here is the percentage improvement that we get for those C states in comparison to the power that we would get from optimal constrained resistive control. So we're getting quite large improvements, usually between sort of 3 and 10%. You will see that's one that's huge of our 1,500. That's basically because we're dealing with very small numbers here. Okay. Also, another thing we've been working on is the power quality aspect from this array of WECs. So if you've got your array of WECs connected to a weak rural network, then you can get large fluctuations. So you want to try and smooth out those fluctuations in the network. And this is some work we did. So we had an array of 6 WECs all interacting electrically and hydrodynamically using the time domain hydrodynamic model. We've got some defig generators in this case. And here we show the effect of spacing between the converters and also on the added inertia. We can add some inertia to the generator, and both those result in smoothing. So you can see as we add more inertia to the defig, then we can get this smoothing, and that's good for our network. Okay, some other work. This is some work from the DT Ocean, EU-funded DT Ocean project. And we've got this techno-economic analysis to assess the transmission options for the connection between the farm and the onshore link. Okay? So here we show, this is what we're actually looking at. So it's this part here between the offshore substation and the shore landing, and it's techno-economic analysis. Within the technical part, we're looking at supply quality constraints like voltage constraints. Also, within the offshore substation, we're looking at the optimal sizing of reactive power compensation. Basically, you don't want reactive power, you want real power fed down the cable. So we've done that. On the economic factors, we've got component installation costs and the cost associated with electrical losses. So here's an example. So we're looking at the percentage energy loss over a year for different farm sizes and different distances from shore at 2 different voltage transmission levels. Okay? And I said, as we also looked at the economic factors. So here we have the relative costs of the transmission network with reference to a base case of 1 megawatt farm 10 kilometres from the shore with a 11 kV network at those two different transmission voltages. Okay, now for something completely different. This is another EU-funded project that we're involved in. I talked about this last year as well, but just update you on what we've been doing. A lot of you won't have been here last year, so we'll need to show you what we're actually doing. So these are wave energy converters with the power takeoff replaced with what we call these dielectric elastomer generators. And I've just got a little video here to show you what. These are the various partners in this project. So we have this video, if it's going to work. So an elastomer is just basically a rubber or acrylic thing that you can stretch and relax. We take compliant electrodes, we put it on top, we stretch it, we charge it, and then as we relax, the voltage increases and we discharge it. So it's basically a variable capacitor that we're using to generate electricity. So within Polywec, we looked at two different types of wave energy converters with dielectric elastomer generators. Here, the first generation was just existing concepts with retrofitted dielectric elastomer generators on them. So buoy, poly OWC, and a poly surge device. Also, the more promising one of these, what we call second generation Polywecs, where we actually have direct contact between the dielectric elastomer and the fluid. So we're moving on to looking at them. So last year, I showed you some results on the poly OWC that we did in the tank, and that was a non-optimized one. That was done, we just retrofitted a dielectric elastomer onto it. But here we now optimized it. We've impedance matched the dynamics of the OWC and the dielectric elastomer. We've also changed the hydrodynamics of the collector with this added mass duct in here. And you see, one thing I should emphasize, these are fully functional tests. We're actually producing electricity here. With a lot of model testing of wave energy converters, you cannot scale down the PTO, but you can with this. So we are producing electricity. So we're producing 0.67 watts. That corresponds to wave-to-wire efficiency of 20% and a full-scale power of 270 kilowatts. Now, another thing we've done with this is the energy harvester controller has been improved. So that's our original network here. But what we actually do is we add in a parallel capacitor, and that allows us to get more power out. This graph here, it's a charge voltage graph. A straight line on the graph represents a constant capacitance, which is basically a variable capacitor. So what you do when you charge, you go up this line, then you let it, so that's it fully charged, then you let it relax, and then it comes back down this line. And that area there is the energy you get out. But actually, if you add in this parallel capacitor, we can actually do this, perform this loop here. This line here, this blue line here, that's the buckling limit. We can't go beyond that, but we can get more power out. Oops. So the other thing we've done is we've looked at floating OWC up in flow wave. This is a non-optimized, we've just retrofitted dielectric elastomer onto the top of an existing model floating OWC. So we're only getting 10% wave to wire, but that will be improved when we optimize the configuration. The other thing we've done, we've tested it in extreme seas. So on the left here, hoping that we're not going to rupture the dielectric elastomer, and we've also tested it in irregular seas. And this is what this trace is here. It's difficult to know in irregular seas when to charge and discharge the dielectric elastomer. Okay, so to the modelling, and you might ask, this hasn't got anything to do with arrays, but actually the modelling is very similar to arrays because it's basically multi-degree of freedom, multi-mode modelling. So this is just an example. So the modelling, we have to do hydrodynamic, elastic, electrical modelling. So here we just got a vertical frame on the seabed with a dielectric elastomer stretched across it. And this figure just shows the panelling for the numerical method that we're going to use. And what we do to represent the deformation of the membrane is we just do supervision of modes, basically, within WAMET. That's multiple modes, multiple degrees of freedom. It's very similar to modelling an array. People will have seen this diagram, this animation before. I was trying to produce a time. This is a frequency domain animation. In order to do the proper simulation, we need to have a time domain because we've got nonlinear PTO forces. Fortunately, I didn't have time to finish off the time domain simulation, so you can just imagine it's a time domain one. So we have an irregular C coming in here. We're just panning around the camera to see the distortion of the dielectric elastomer. Okay. So the final bit we're going to talk about is work that we're just starting. Literally, we had a meeting about it yesterday. So we're going to do wave-to-wire modelling of tidal turbine array. You've seen some of that already. So we're going to do experimental investigation of hydrodynamic and electromechanical interactions between turbines and electrical network. And it's a 3-turbine array. So this was a flow wave animation that they've very kindly let us borrow, and this shows exactly what we're going to do. So we'll have 3 turbines in flow wave, and we can obviously vary the direction of the current, we can vary the direction of the waves relative to the current, and that's exactly what we're going to do. So this is following on from the work in XMed. So this is the turbine that colleague Gregory Payne produced, a very good turbine indeed. And so we're going to build another 2 turbines based on the experience that Greg has learned. We're going to improve the sensors at the bending moment, at the root bending moment sensors, and also the speed control. The other thing we're going to do is we're going to link it to, we have a dedicated network emulator that will link this to, so we can have a very good test indeed. The other thing, within the XMed project, I think we had wave and current in the same direction. We can, of course, within this project, within flow wave, we can have wave and current coming from different directions. So, and yeah, as I say, the tests are going to be done in flow wave. So, yeah, just leave you with some animations. So.
This production is brought to you by the University of Edinburgh.